Somewhere in the dark abyss of the constellation Pegasus, 280 million light-years from the tiny blue marble we call home, one of the grandest, most violent, and most breathtaking spectacles in the known universe is unfolding. There, where ordinary human imagination dissolves into infinity, where distances are so vast that the word far loses all meaning, 5 galaxies have come together in a deadly, slow, and inevitable dance. They are called Stephan's Quintet, a name that brings a shiver even to those long accustomed to looking at the night sky through telescopes and seeing not just stars, but entire universes. 5 galaxies, 5 giant island systems, each containing anywhere from a few tens of billions to several hundreds of billions of stars. 5 worlds, each of which could be considered infinite on its own. And yet, obeying the relentless hand of gravity, they all converge in one place.
They reach for each other, penetrate each other, destroy, and simultaneously create something new, terrifying, and majestic. This is not a metaphor. This is a literal, physical reality, captured in images from the world's most powerful telescopes, calculated in the formulas of general relativity, and confirmed by X-ray observatories and radio telescopes. Stephan's Quintet is a true battle of galaxies, and it is happening right now, in real time, though the word now requires clarification. What we observe today actually happened nearly 300 million years ago. That is how long it took for the light to cross the void between this cosmic carnage and our eyes. The Quintet was discovered in 1877 using the telescope at the Marseille Observatory. Even in those early days, when astronomers did not yet know that nebulae were not clouds of gas within our own galaxy, but separate galactic systems, something about this cluster of 5 barely visible smudges caught their attention. Today, it is officially cataloged as HCG 92, the 92nd object in the Higgson Compact Group catalog, a collection of tightly bound galactic systems whose fates have become inseparable across cosmic time.
But to truly understand the Quintet, one must first understand each of the 5 galaxies individually, with their characters, differences, and unique cosmic biographies. And here, the first fascinating mystery begins. One of the 5 galaxies is an imposter. She only appears to be a member of this society. In reality, she is somewhere else entirely, 40 times closer to us than all the other 4. She simply fell into the field of view by chance, like a stranger in a group photo at someone else's wedding. This outlier is galaxy NGC 7320, and her presence in the Quintet is one of the greatest illusions in all of astronomy. NGC 7320 is located only 40 million light-years away. In astronomical terms, that's practically within reach. It is a small spiral galaxy, quite modest in size, with a well-developed structure and many regions of active star formation glowing in blue and purple, the classic colors of young, massive stars. When we look at images of the Quintet, NGC 7320 looks like a full member, positioned in the lower left corner, indistinguishable from her neighbors at first glance.
But telescopic observations measuring redshift, the Doppler shift of spectral lines used to determine speed and distance, show definitively NGC 7320 is receding from us at a speed of about 800 kilometers per second. Her 4 neighbors are receding at speeds between 6,600 and 6,700 kilometers per second. The difference is colossal. NGC 7320 is simply in the foreground, standing between us and the true Quintet, appearing as a member only because of a cosmic coincidence of alignment. So the true gravitationally bound ensemble consists of 4 galaxies: NGC 7317, 7318A, 7318B, and 1719. These 4 are a true family, locked in a single system by relentless gravity. They revolve around each other, pull, push, exchange matter, tear each other's spiral arms, and slowly, over hundreds of millions of years, merge into something new. And right now, in the very moment we are observing, this system is experiencing one of its most dramatic events: an invasion. NGC 7318b is the invader. Although it is a member of the group, it is moving through it at a speed exceeding 800 kilometers per second relative to the surrounding environment. Think about that number: 800 kilometers per second. In just 1 second, this galaxy travels a distance a high-speed train would take hours to cover. In 1 hour, it moves further than the diameter of the moon. It is crashing into the hot gas filling the space between the other members, creating one of the largest shockwaves in the known universe.
The shockwave resulting from this collision is not a collision between the stars themselves. Stars almost never collide, even during a merger, because the distances between them are so vast. Instead, it is a collision between NGC 7318b and the intergalactic gas filling the group's space. This gas is heated to temperatures of tens of millions of degrees and begins to glow in the X-ray spectrum. The Chandra X-ray Observatory captured this brilliant emission as a grand arc stretching across the entire group. This arc spans tens of thousands of light years, essentially the entire width of the group. But imagine what happens where the shockwave meets the intergalactic gas. The gas is compressed, heated, and turbulent. In the areas of greatest compression, where the density of the gas spikes, star formation begins. This is one of the most amazing cosmic paradoxes. Destruction and violence give birth to new creation. The collision and invasion bring chaos, but the compression of gas triggers a gravitational collapse. From these turbulent clouds, new stars are born, young, bright, and blue. In images of the Quintet, you can clearly see long chains of young star clusters, like blue beads, stretching along the zones of active interaction.
Now let's look at each galaxy individually, reaching into the very matter of this cosmic tapestry. NGC 7317 is the southernmost of the 4 interacting galaxies. It is an elliptical galaxy, slow, old, and devoid of spiral arms or the large amounts of cold gas needed for active star formation. Its color is yellowish, typical for systems where most stars are already old and the young blue giants have long since burned out. NGC 7317 looks relatively calm compared to its rowdy neighbors. It sits slightly apart from the most active zone of interaction and suffers less deformation. However, even it is not untouched. Tidal forces from its partners are warping its shape and stretching its outer layers. In the distant future, as the group continues to merge, this deformation will only grow. NGC 7319 is a more complex and much more active galaxy. It is a spiral system, classified as a Type II Seyfert galaxy, meaning its center hosts a supermassive black hole actively devouring surrounding matter. This creates what we call an active galactic nucleus, or AGN.
The AGN of NGC 7319 is a tiny, incredibly bright and energetic region where matter spirals into the black hole, heating up to astronomical temperatures. It radiates across the entire electromagnetic spectrum, from radio waves to hard X-rays. The accretion disk around this black hole is one of the brightest X-ray sources in the entire group. But that's not all. The galaxy is also pierced by thin dust lanes and has long tidal tails, gravitational arms stretched out into space by the pull of its neighbors. NGC 7318A and 7318B are a pair that stands out even within the Quintet. At first glance, they look as if they have merged into one, but they are actually still in the middle of a violent interaction. NGC 7318A is an old elliptical galaxy, similar to 7317, filled with aging stars and very little cold gas. NGC 7318B, however, is a different story. This is the invader we mentioned earlier, slamming into the group at that staggering speed of 800 kilometers per second. Even though they appear almost inseparable in photos, spectral observations reveal the truth. Each has its own distinct redshift and velocity. The difference of several hundred kilometers per second between them is the smoking gun that proves 7318B is rushing through the group much faster than its companions.
Stephan's Quintet exists in a zone of true cosmic madness. The space between these galaxies is filled with hot, rarefied gas, molecular clouds, and an invisible but omnipresent force, dark matter. Dark matter is the mysterious substance that doesn't interact with light, making it invisible to telescopes, but it reveals itself through gravity. It acts as the invisible glue holding this entire ensemble together. Without it, the galaxies would have flown apart long before they ever reached their current positions. Perhaps the most shocking discovery in the Quintet is a giant filament of molecular hydrogen stretching across the entire group. Under normal intergalactic conditions, molecular hydrogen, H2, shouldn't survive. The radiation from young stars' active nuclei usually tears these fragile molecules apart. Yet in the Quintet, it forms a structure hundreds of thousands of light years long. How this gas survives such radiation and gravitational violence without being destroyed is still one of the greatest unsolved mysteries of the group.
No observation of Stephan's Quintet had as much impact on the world as the images released by the James Webb Space Telescope in 2022. These images instantly went viral, appearing in everything from scientific journals to social media feeds across the globe. The Webb telescope is an infrared powerhouse. Infrared light can pierce through dust clouds that are opaque to our eyes, revealing stars and structures hidden behind a veil. With its 6.5-meter primary mirror, Webb looked at the Quintet with unprecedented precision. What it revealed surpassed even the most optimistic expectations of the scientific community, showing us the bones of the galaxies and the raw heat of the cosmic battle in a way never seen before.
In Webb's images, the shockwave from NGC 7318B appears in all its terrifying beauty. A giant arc of hot gas, heated to millions of degrees, stands out vividly against the background of colder structures. Next to it are massive flows of molecular hydrogen, illuminated by the shockwave and glowing in the infrared. It resembles the effect of a sea wave crashing against a rock, creating sprays and foam that fly in all directions. Only instead of sea foam, there are billions of tons of hydrogen gas, and instead of seconds, the process takes millions of years. The zones of active star formation, where the gas is compressed and begins to collapse under its own gravity, sparkle in pink and red, the signature glow of ionized hydrogen lit by the ultraviolet light of newborn stars. But the most astonishing discovery by Webb in the Quintet was the incredibly detailed images of tidal tails and bridges between the galaxies. These tails are long threads of stellar matter stretched far beyond the galaxies by tidal gravitational forces. Webb revealed their internal structure with such clarity that individual star clusters embedded within these tails became visible. Some of these clusters are tidal dwarf galaxies, small, independent galactic systems being born from the matter torn out of the parent galaxies during their struggle. Thus, a catastrophic collision does not just destroy, it literally gives birth to new galaxies, albeit much smaller ones. Speaking of tidal structures, we must mention a particularly striking object, the Old Tidal Arc, or Northern Tidal Tail. This structure stretches for tens of thousands of light years from NGC 7319 and is the result of an ancient gravitational interaction between the group members. Its age is estimated at billions of years, meaning it was born when the quintet was just beginning its internal dance. Today, this arc serves as a geological layer, a preserved record of an ancient encounter written into the very matter of intergalactic space. The dynamic picture of the entire ensemble is equally fascinating. Supercomputer simulations that account for gravity, dark matter halos, gas, and stars show that the fate of the quintet is sealed. Sooner or later, all four main galaxies will merge into one single giant elliptical galaxy.
This process will take another few billion years, but on a cosmic scale, that is not a long time. The current violent phase we observe, the invasion of NGC 7318b, the massive shockwave, the burst of starbirth, is merely one episode in this long, majestic tragedy of merging. Computer simulations allow us to not only recreate what we see now, but also to rewind and fast forward time. Rewinding helps us understand how the group formed over billions of years. Fast forwarding shows us the final shape of the merged system. Interestingly, even NGC 7320, or Imposter, located 40 times closer, will eventually continue its own path and leave the quintet's field of view, existing peacefully in its own corner of the universe, unrelated to the turbulent ensemble it once seemed to join. Compact groups like Stephan's quintet are relatively ephemeral formations. They are rare configurations where galaxies are so close that the distances between them were comparable to the sizes of the galaxies themselves. These groups are living laboratories of galactic evolution.
The quintet is especially valuable because we see it in such an active, dynamic phase. We are witnessing the merger of 7318A and B, the invasion shockwave, the tidal bridges, and the active core of 7319 all at once. It is a place where we can study how galaxies collide, transform, and eventually become one. The stellar catalog of the quintet is surprisingly diverse. Here you find stars of all generations, from the ancient ones that formed at the dawn of galactic existence billions of years ago, to the very young, born literally yesterday as a result of gas compression by shockwaves. The old stars are concentrated mostly in the galactic cores and long tidal tails, where conditions remain relatively calm. Meanwhile, young blue stars decorate the zones of active interaction, places where gravitational and dynamic violence have squeezed the gas so tightly it began to give birth to new cosmic inhabitants. Among the new star clusters born from the quintet's struggle, the superclusters, or young massive clusters, deserve special attention. These are incredibly dense concentrations of young massive stars, containing thousands to millions of solar masses.
While in normal spiral galaxies, these clusters form mainly in the arms or near the core, in Stephan's quintet, they are scattered everywhere, along tidal tails, in intergalactic bridges, and within the X-ray arc. This is a unique firework display of starbirth, ignited by brutal gravitational forces. The massive stars born in these superclusters live short lives, only a few million years, before exploding as supernovae. A supernova is one of the most energetic events in the universe,
the collapse of a massive star releases as much energy in seconds as our sun produces in its entire 10 billion year lifespan. The shock wave from a supernova spreads through the environment, compressing even more gas and triggering new waves of star birth. Thus, star formation in the Quintet becomes a self-sustaining process. The shock wave from the invader NGC 7318b triggers a burst of stars. Those stars explode as supernovae, their shock waves compress more gas, and the cycle continues in an endless chain of cosmic violence and creation.
Dark matter in Stephan's quintet plays a role just as fundamental as visible matter, but far more mysterious. Each of the 4 main galaxies is surrounded by its own halo of dark matter, an invisible sphere several times larger than the visible galaxy itself. When these galaxies interact, their dark matter halos also collide, but in a completely different way than gas or stars. Stars and gas feel each other. Gas crashes into gas, heating up and creating shock waves. Dark matter, however, passes right through other dark matter, almost without interaction. It only feels gravity. As a result, the dark matter halos of different galaxies overlap and penetrate each other, blending into the space of the group. The result of these interactions is that today, the dark matter in the Quintet is no longer the property of individual galaxies. It has partially declared itself the property of the entire group. A common dark matter halo is forming, encompassing all 4 galaxies. This is further proof that the Quintet is a mature system. In newly formed groups, dark matter is still concentrated around individuals, but in adult systems like this, it is already shared across the entire ensemble.
X-ray observations from the Chandra and XMM Newton telescopes have revealed yet another layer of complexity. The hot intergalactic gas in the group contains significant amounts of heavy elements: oxygen, neon, iron, and silicon. These elements were blown out of the galaxies by supernovae and stellar winds. Studying the chemical composition of this gas helps us understand how the intergalactic medium is enriched with the heavy elements necessary for the formation of planets and, eventually, the complex chemistry of life. The active galactic nucleus, or AGN, of NGC 7319 is a topic of study all its own. While supermassive black holes exist in the centers of almost all large galaxies, including our own Milky Way, where Sagittarius A star holds the mass of 4 million suns, not all of them are active. The black hole in NGC 7319 is hungry. It is surrounded by an accretion disk, a structure of superheated gas spiraling inward. As the matter becomes more compact and hotter, it radiates a colossal amount of energy just before crossing the event horizon and vanishing forever.
When the James Webb Space Telescope pointed its gaze at the Quintet, it revealed something incredible. Through the gas and dust of NGC 7319, it didn't just see the galaxy's core. It spotted NGC 7320c, another galaxy located even further away. This background galaxy sits approximately 800 million light-years from us. The fact that Webb can see it clearly through the foreground matter is a brilliant demonstration of its incredible resolution. It can see objects through other objects, if they are bright and compact enough. The discovery of molecular hydrogen, H2, in the Quintet is one of the most significant scientific breakthroughs associated with this object. Unlike hot ionized gas, which glows pink, or neutral atomic hydrogen detected by radio telescopes, molecular hydrogen is observed in the near-infrared. The mystery is that the bulk of this molecular hydrogen isn't inside the galaxies, where it would be safe. It is floating in the intergalactic space between them. Right where the shockwave from NGC 7318b passes through the superheated intergalactic gas, the molecular hydrogen somehow survives.
This creates a true puzzle for theoretical astrophysics. In the same zone, we find 2 seemingly incompatible components:
superheated ionized gas at tens of millions of degrees, and relatively cool molecular gas at just a few thousand degrees. How can they exist in the same place at the same time? One theory suggests the shock wave is patchy, traveling through an uneven medium. In denser areas, the wave slows down and fails to heat the gas as much as in the thinner surroundings. The molecular hydrogen might be hiding in these islands of dense gas, protected from the most violent effects of the shock. Another theory credits magnetic fields, which may cushion the gas and prevent it from breaking apart. Radio telescopes like the VLA in New Mexico and Merlin in the UK add another dimension by tracking neutral atomic hydrogen, HI. This is the raw material for molecular hydrogen and, eventually, for starbirth.
In Stephan's quintet, the distribution of neutral hydrogen is striking. Most of it is located in the tidal tails and intergalactic space, rather than within the galaxies themselves. This proves that galactic interactions are incredibly efficient at ripping the gas out of galaxies and scattering it across the entire system. Radio observations have revealed a massive complex of neutral hydrogen to the north of the quintet that isn't tied to any single galaxy. It simply floats in intergalactic space, a silent witness to countless ancient interactions. The mass of this wandering gas complex is measured in billions of solar masses. It has enough material to form a full-fledged dwarf galaxy, should conditions ever favor a gravitational collapse. For now, it remains a sprawling cloud of cold gas, carrying the memory of past cataclysms within its structure. Stephan's quintet has played a vital role in developing and testing theoretical models of galactic interactions. The first serious numerical simulations of these collisions date back to the 1980s and 90s. While limited by the computing power of the time, they already showed the general picture. 4 galaxies with masses of hundreds of billions of suns, drawn together by relentless gravity.
Today, supercomputers and n-body algorithms allow for simulations that precisely replicate the quintet's observed characteristics: the shape of the tidal tails, the distribution of gas and dark matter, and the unique kinematics of each galaxy. Modern simulations of the quintet are so detailed they account for gas dynamics, the movement and behavior of gas, including heating, cooling, star formation, and the feedback from supernovae and active nuclei. These hydrodynamic simulations require immense computational resources, but they match our observations with stunning accuracy. They have successfully recreated the shape of the X-ray arc from NGC 7318b's shockwave, and even the specific distribution of star clusters within the tidal tails. Stephan's quintet is as much an aesthetic object as it is a scientific one. Images captured by various telescopes have become classic icons of astronomical photography. The 2009 Hubble image became an instant internet sensation, showcasing the galaxies in all their glory. The yellowish cores of old elliptical systems, the blue chains of young star clusters, and the pink clouds of ionized hydrogen. In 2022, the James Webb Space Telescope surpassed even Hubble's detail. By peering through the infrared, it revealed structures just a few dozen light-years across, even at a staggering distance of 280 million light-years. The power of these images lies in their natural beauty: the spiral structures reflecting density waves, the elegant curves of tidal tails resembling seashells, and the bright blue pearls of young stars against the yellowish cotton of old ones. All of these appeal to the same principles of symmetry and harmony that define human aesthetics. The only difference is the scale. What we see in the quintet happens on spatial and temporal levels that exceed human imagination by billions. What does the future hold for Stephan's quintet? Computer simulations provide an answer that is both predictable and thrilling. In a few 100 million years, a mere blink in geological time, NBC 7318b will complete its invasion and draw closer to the other members of the group. The shockwave will gradually fade, but its legacy, the burst of star formation, the chemical enrichment of intergalactic gas, and the birth of tidal dwarf galaxies will remain forever written into the fabric of the system.
Eventually, gravitational friction will slow down all 4 galaxies, and they will begin to move more tightly toward their common center of mass. NGC 7317, which today seems to stand apart from the main battlefield, will also be sucked into this vortex. NGC 7319 will either switch off its active nucleus as its gas supply is depleted, or conversely, receive a fresh flow of matter from its partners, igniting its black hole even more brightly. In a few billion years, all 4 galaxies will merge into one single large elliptical galaxy. This final product will be much larger than any of its original components and will have a completely different morphology. Instead of spiral arms and complex structures, it will be a smooth, steady ellipsoid filled with old stars, a dead elliptical galaxy where active star formation has ceased because the cold gas has either been consumed or blown away. But that is far in the future. Today, Stephan's Quintet is in the heat of its most dramatic adventure. The shockwave from NGC 7118b is still tearing through the intergalactic gas. The hot X-ray gas still glows in radiation invisible to the human eye, but clearly captured by our instruments. New stars are still being born along the shock fronts. The molecular hydrogen in its great filament stands guard, emitting its characteristic infrared shimmer. And from Earth, these 5 galaxies, 4 interacting and 1 imposter, still appear as a tight cluster of smudges in the constellation Pegasus, urging us to uncover ever newer secrets.
Interestingly, Stephan's Quintet became known to the general public long before it began to be studied in detail by modern methods. Back in 1946, it appeared in the film It's a Wonderful Life. The director used images of the galaxies as a backdrop for heavenly scenes, although at that time, most viewers did not even suspect that they were seeing a real astronomical object. This cultural celebrity became an additional push to popularize the quintet in mass culture, and today it is one of the most recognizable astronomical objects in the world, on a par with the Orion Nebula and the Andromeda Nebula. From a scientific point of view, Stephan's Quintet is a unique natural proving ground for studying several fundamental problems of modern astrophysics. The first is the mechanism of kinetic energy transfer from gravitational interactions to the thermal energy of intergalactic gas. When NGC 7318b moves at a speed of 800 kilometers per second through the group, a huge amount of kinetic energy passes into heating of the gas, and partly into mechanical work that compresses clouds and triggers star formation.
The second fundamental problem is the role of magnetic fields in the intergalactic medium of compact groups. Magnetic fields that permeate galaxies and the space between them are an important but still poorly studied component. In zones of shock waves and turbulent mixing of gas, magnetic fields can strengthen, change their direction, and affect gas dynamics. In Stephan's Quintet, polarimetric observations in the radio range allow mapping the distribution and orientation of magnetic fields, and these maps show an extremely complex, tangled structure reflecting the turbulent dynamic history of the system. The third problem is the feedback of the active galactic nucleus of NGC 7319 on the surrounding gas. It is known that AGNs are capable of blowing out bubbles of hot gas into the intergalactic medium, thereby preventing gas cooling and star formation, a process known as AGN feedback. In Stephan's Quintet,
This process can interact with feedback from the NGC 718b shockwave and from supernova bursts, creating a complex, multi-layered system for maintaining the thermal balance of intergalactic gas.
Observations of Stephan's quintet in the gamma-ray range represent a separate, fascinating area of research. Gamma rays, the most energetic radiation in the entire electromagnetic spectrum, can arise from the acceleration of charged particles in shock waves. The shock wave in Stephan's quintet is such a powerful particle accelerator that some theorists predicted the possibility of detecting gamma radiation from this object. Although the detection of such a signal is still awaiting confirmation, the very fact that the quintet is considered a potential source of gamma rays speaks to the colossal energies released during these interactions. Interestingly, Stephan's quintet is a relatively young system in the sense that it formed quite recently, at least compared to the scales of the universe. Earlier and more developed compact groups that existed in the young universe 8 to 10 billion years ago have long since completed their merger and turned into giant elliptical galaxies. Stephan's quintet is a living example of what such systems looked like at an active stage of their development. By studying it, we are essentially studying the past of today's more quiet galaxies.
If we imagine an observer located somewhere inside the quintet system, say on a planet orbiting one of the stars in the tidal tail of NGC 7319, the sight opening before them would have nothing in common with the night sky we see from Earth. Instead, the imaginary observer would see a grand firmament where giant bands and arcs of stellar matter stretch in all directions. Several galaxies would be visible to the naked eye, not as faint nebulous spots, but as vast fields of light occupying a significant part of the sky. In one direction, the yellowish elliptical mass of NGC 7317 would appear like a giant yellow fog. In another, the bluish glow of NGC 7318b, with its zones of active star formation shimmering in blue and purple. Near the horizon, the X-ray arc, invisible to the eye but felt as streams of charged particles. Above all this, a giant filament of molecular hydrogen would faintly shimmer in the near-infrared, piercing the space between galaxies like a colossal web. Such a sky would be both terrifying and beautiful. Terrifying because there is no safe place in the quintet to sit and calmly observe the stars. Shock waves, radiation from the AGN of NGC 7319, and a constantly changing gravitational field would make it an extremely aggressive environment. Beautiful because everything happening in the quintet is a manifestation of the fundamental laws of nature in their extreme expression. Gravity, gas dynamics, nuclear physics, and electromagnetism interact here with such intensity that they turn into a true masterpiece of nature. Why does Stephan's quintet continue to attract such attention, both scientific and general? The answer lies in several aspects. First, it is an unsurpassed natural experiment in galactic interactions where multiple physical processes can be studied simultaneously. Second, it is one of the closest and brightest objects of its kind, providing incredibly detailed data. Third, every new telescope and every new observation range reveals something new structures, new processes, and new mysteries. Fourth, and perhaps most importantly, it is a perfect illustration of the most fundamental theme in galactic astrophysics, the theme of transformation, evolution, and change. Galaxies are not static objects. They are born, evolve, interact, merge, and die, or rather transform into something new. Stephan's quintet is a visual and scientifically documented demonstration of this transformation.
Looking at images of the quintet, we are not looking at a static photograph of the cosmos, but at a frame from a movie, one that has been playing for billions of years and will continue for billions more. The fact that we live at the exact moment that NGC 7318b is crashing into the group is an amazing coincidence that makes our generation witnesses to one of the grandest spectacles in the universe. Stephan's quintet also helps us understand the early stages of the universe. During the cosmic dawn, the universe was much denser and hotter. Galactic collisions were the norm, not the exception. By studying the quintet, a relatively close and well-observed object, we can extrapolate our findings to the distant universe. The quintet is a kind of Rosetta Stone for decoding early galactic evolution. Comparing distant faint systems with the well-studied quintet allows us to understand how galaxies formed throughout cosmic history. There is a detail that symbolically connects everything we've discussed. The molecular hydrogen in the shock zone is the matter from which stars are born, and thus, indirectly, planets and heavy elements. The iron in the hot intergalactic gas was forged in the hearts of long-dead stars. The carbon, oxygen, and calcium were once the core of massive stars that exploded as supernovae. These are not just abstract elements. They are the same atoms that make up mountains, water, air, and the cells of living beings. Stephan's quintet is a demonstration of the cyclical nature of matter. Gas births stars. Stars forge heavy elements and scatter them into space, and those elements become part of new clouds, new stars, and new planets. In the violent conditions of the quintet, this cycle is accelerated to the maximum. What takes billions of years in quiet parts of the universe happens here in millions. The quintet is the universe in a hurry to live. There is something incredibly striking in this. We, existing in a quiet corner of an ordinary spiral galaxy, look into the sky and see a stage where galaxies fight and love simultaneously, where destruction and creation are inseparable, and where the largest structures in the universe, containing trillions of stars, move and transform according to the same laws of physics that govern the fall of an apple. Stephan's quintet is a mirror reflecting the universe itself in all its complexity, contradiction, and majesty. The sky above us is not a quiet, still backdrop. It is an arena where battles take place, compared to which all human conflicts are a drop of water against the ocean. But these battles are not fought for destruction. They are fought for transformation, for the birth of the new from the old, for the incessant, endless dance of matter and energy through space and time.
5 galaxies in the constellation Pegasus, 4 of them in a deadly, beautiful embrace of gravity. 1 imposter, simply passing by, unaware of its role in our perception of this spectacle. A shock wave, hundreds of thousands of light years long. Molecular hydrogen mysteriously surviving the hell of collisions. Hot X-ray glow from billions of tons of heated gas. Thousands of new stars being born right now. A black hole in the heart of NGC 7319 greedily swallowing matter. Dark matter invisibly holding the ensemble together. Tidal tails and bridges stretching across the void. Dwarf galaxies born from the debris. A future merger that will one day result in a single giant elliptical galaxy. This is Stephan's quintet, one of the grandest spectacles to ever occur in this universe, and one of the most precious treasures preserved for us by the infinite cosmic arena. Looking at it, it is difficult to remain indifferent. It is hard not to feel both our infinite smallness and at the same time the amazing privilege of being witnesses to such a sight, to have eyes and minds capable of grasping even a small part of the grand reality that is the universe. Stephan's quintet speaks to us in a language of physics and mathematics. But behind this language lies something much deeper, the inexplicable yet palpable beauty of existence.